Hey.
Yes, okay, there we go. All right, okay, so welcome everyone. It's a pleasure today to be hosting Jessica Dempsey again. So for those of you who weren't here yesterday, I will give a very brief introduction. So she gave a successful EDI seminar yesterday, and today she will be speaking about the future of radio astronomy with the perspective of Astron. So Jessica Dempsey was recently, about 1 year ago, appointed director of the Netherlands Institute for Radio Astronomy, Astron. She spent over a decade in Hawaii as deputy director of the JCMT. And while at the JCMT, she was a member of the Event Horizon telescope team. She has a background in radio interferometry with a scientific focus on wide field transient surveys of the galaxy at radio wavelengths and on the frontiers of big data science pipelines for astronomy. She has a passionate commitment to creating greater diversity, equity, and opportunity at all levels of astronomy and to enhancing opportunities for girls to become future leaders in science and technology careers, which was the topic of yesterday, but today we will hear about the future of radio astronomy. Thank you.
Thank you. Hey, thank you very much. I've really enjoyed having a couple of days to get to know you all a little bit. And today, I'm going to sort of give you a little bit of a background to Astron. And you can see this gorgeous image here of one of the supertubs out in the Dutch wilderness that is the platform for what is actually the existing currently most powerful radio telescope on the planet at these wavelengths. So I'm going to give you a little bit of a background of Astron itself, and I'm going to talk about the two major radio astronomy observatories that Astron is committed to now operating, advancing the instrumentation of, and building in terms of both LOFAR and SKA. Then what I want to do with you is I want to take you on a little bit of a journey into the future and just give you an idea of the scope and scale to which radio astronomy is going to be expanding within the next decade. And because of the scope and scale of this expansion, I want you to start thinking with me about the opportunities scientifically for us in what is going to be an entirely new field and an entirely new level of investment and capability than we've ever seen before from the ground at these wavelengths. So this is Astron. There in the corner, you can see the beautiful Bungalow telescope. And behind that, the Astron Institute. It's nestled in, I didn't really imagine that you could have distant places in the Netherlands coming from Australia. It seemed all very close, but actually it still does feel like you're in the middle of the woods because we're in the Bungalow National Forest. We have about 200 people that we host, both in our own organization, Astron, but we also have the Jive, Eric. This is the operational entity for research infrastructure that runs the European VLBI network across Europe. We also host a portion of NOVA. NOVA is an astronomy consortium that takes into account all of the astronomy groups across the Netherlands university landscape. But in particular, we host the optical and infrared instrumentation group. For example, right now, what they are leading is the design and build of a portion of the spectrometer for MATIS, which is one of the first light instruments for EOT. It says here that we have a 60-year history. In fact, Astron will be celebrating its 75th anniversary next year. And it is in some ways the birthplace of radio astronomy in its current form, including things like Wi-Fi was actually invented in the building, which I just found out about the other day. So we have these three different arms. We have our business and design arm. We have an astronomy and operations element here. So we have a very large science group in and of themselves. And then we have innovations and systems team, which is engineering, software development across a range of different radio technologies. So we have sort of, Astron is sort of at a bit of a crossroads right now. We really did head up against some very big challenges at the end of the pandemic. And this meant we had to look at our portfolio of what we were doing. And in fact, we had to step back a little bit. One of the things which was a frustration for us and the sacrifice we had to make was actually that we finished the aperitif phased array operation at Westerbork, just before I arrived, actually, at this time last year. So this did actually reduce the capacity and the abilities of the Westerbork operations. And that was simply because we have so many other things on the plate. And the major one, which I'll talk about at a bit more length later, is we have the huge upgrade of LOFAR to LOFAR 2. We have our ERIC, our research infrastructure for Europe for LOFAR underway. And as of December, SKA construction, after 30 years of conversation, is finally underway. So all of these things are becoming real, and we had to make some changes. So Astron, really, I think one of the things that it has always managed to do is, because it's constantly on the bleeding edge of radio technology development, it really has managed to, for its relatively small footprint, always maintain a technology and science edge. And so you see down here the sort of evolution of this. 1956, the Bungalow telescope, for 2 weeks, it was the largest radio telescope on the planet. And then John will bank open. You're like, well, okay. But it actually did some incredible science. And in fact, it was then sort of decommissioned and had fallen into a bit of disrepair. We then had a volunteer group resurrect it and did a beautiful restoration of the telescope nearly 10 years ago now. In fact, I think it's in better shape than it was when it was originally built. And they now still use this for dedicated student projects. They tracked the lunar probe, for example, and things like this. So it's actually still a functional telescope. Stepping into then, you had Westerbork, which was built in the late 1960s and was one of the leading interferometry arrays in the low gigahertz regime, all the way up until now. And as I said, the phased array aperitif was the last major upgrade for the facility. But right now, it is still in a semi-operational state. We have 2 telescopes which are still working for the EVN and single dish development. And then, of course, LOFAR was the next stepping stone here in these frequencies. And it was finally on first light roughly around 2010. And so, we're well over a decade now of full operations for LOFAR, and I'll talk to you about that a bit more. And of course, by 2030, we're going to have SKA in full operation. So one of the ways I think I like the description inside of Astron is we are pride ourselves on being an end-to-end radio facility technology. Every single thing from the collection end, so front-end development of radio astronomy, photonics, filtering, beamforming, all of this can be built in-house. You can then, all the way through the radio chain, there is the expertise in Astron to be able to do development and build in these every single stage, all the way through to development of the high performance computing that you need at these frequencies, because the data volumes are just extraordinary. And really, this is something that radio astronomy has yet to properly harness, where you do have point and shoot now at pretty much every other wavelength. Radio astronomy really is still very bespoke. We are now working on making sure that any astronomy at any wavelength could come in and use this facility and not have to somehow figure out what to do with a petabyte of unfiltered visibilities. So LOFAR is really an experiment that was too successful and became an observatory by accident. That's kind of how I kind of think of it. It certainly was at the absolute cutting edge of what we were capable of when it started. I think that's still true. I do think, though, that the reason SKA is now in the development stage it is because LOFAR demonstrated that it could be done. Now it has expanded to having a footprint in 10 countries, more than 50 antennas, but 38 of them, the core of that is in the Netherlands. And right now, and I'm going to go through some statistics, the community is actually quite extraordinary. So this is the ramp up of publications from LOFAR. And what you just see plotted there is you actually see the authorship affiliation of those. And so you can put this in another way. This is a chord chart. On one side here, you see the nationality of the first author of the papers for LOFAR. And on the other side, you'll see the year. And so first you see the increase in papers just in the broadening of the arcs. But the second thing you start to see is the deepening diversity of people who are using and publishing data with LOFAR. In fact, 3 times more publications over this 5-year period. Another way you can measure this is you want to look at what your broad community is like and how has that grown. This is actually a little chord chart GIF showing the increase in the community collaborations. And this is a ribbon where it'll reach from the first author of a paper to the co-authors regions. And so what you want to hopefully see in a healthy community is growing numbers of collaborations between all of your member countries. In fact, this is a 7-fold increase in the size of the community and the collaborations over 5 years. This is essentially unparalleled. If you want to then go and throw it on the world stage, this is putting LOFAR up against every single other facility on the ground at any wavelength. In fact, you don't get on any of these plots unless you're in the top 10% of performance in terms of publication impact at all. And in fact, if you look at the red line, the median impact per paper of LOFAR puts it in the top 10, not in radio facilities, across any wavelength of ground-based astronomical facility on the planet. If you talk about something called an altmetric score, this is a different way. We're sort of moving away from just looking at citation impact as a measure of how useful your science is. Altmetrics take into account social media, news articles, what actually resonates in your science. And when you use this metric, LOFAR pops up even higher on this, and you end up in the top 7. I'm a little controversial with some of the ones that I use, which is if you happen to know how much your telescope operates and costs, you can say, well, if you say, look at this, and this firstly just tells you, this is the total impact of an observatory. So this is when you take that average impact per paper and sum it up over all the papers. So if you put out a lot of papers, Alma, of course, here is going to win big time, always high impact, a lot of high impact papers. VLA, right? Here you can see the VLA. So I would say this is the one to watch in comparison. At least this is in the radio frequencies of something comparable is also up there because of the volume. But if you know what your observatory costs and you divide it, that impact by that cost, you now get per paper, what does it cost per paper for an observatory? And now you look at Sophia and you can understand why they might have closed it down at $1 million US per paper. But look at the difference between LOFAR and VLA. It actually is 10 times more per paper. So you're 220,000 euros per paper with a VLA. It's just 26 for LOFAR. You want to be even more controversial and say, what does it cost for your impact? Per paper cost when you for impact, and you're the top 3 in the world. So it's the little observatory that could. So it also looks simple, yeah? There are no moving parts. It actually looks kind of boring. We really struggle to make this look pretty on our maps because, well, it's not exactly looking like a telescope because it's a digital phased array. All of the beams are formed digitally. It gives you an awful lot of flexibility, but they are really essentially just poles sticking up out of some grass. It doesn't really have the romantic look of the observatory that you would like. However, it is incredibly effective. We have 2 flavors, if you like. We have high band and we have low band. So the low band is 10 to 90 megahertz, high band being 110 to 220 megahertz. And it's a sort of a little difficult to see what the cluster of arrays is there. I have a better version of this in a second. What we then do is we get these high bandwidth fibers. We send our signals to Groningen, a central processing factory there, and we correlate them. And this is where all the time scale is, and this is where the cost is. It's all in the data volumes. Our only limitation is data volume. We use about 1% of the collecting capacity of LOFAR at the moment, because that's all we can afford to process. This is just a little bit of a subset of some of the amazing astrophysics which is coming out of LOFAR at the moment. This is the deepest LOFAR image ever made. 164 hours of observing. This gives you an idea of the data volumes, 4 petabytes of data just for this image. And this is just extraordinary. Over 80,000 radio sources were detected in here, some incredible large-scale emission, and you can just see just a little snapshot of some of the images that are in here. And this is work that when we take to LOFAR 2 is going to be able to enable us to take even deeper images. One of the most mind-blowing areas for me is the fact that we are now an exoplanet potential facility. And so one of the things that you can do, and now we have actually confirmed this with brown dwarf detections, you can actually find the magnetic fields, the circular polarization coming off of aurora. So we're seeing this from solar winds hitting magnetic fields around planets and brown dwarfs. So we do think that this is a way of finding exoplanets at radio frequencies. And the confirmation of this and finding some of this emission, that this is wonderful, right? Because now you can go down and drill down and find these magnetic field protected planets. This is one step closer, of course, to finding planets which are potentially inhabitable. The other thing, which is the long baselines. So we are now out at Poland, for example. We do have these incredible baselines. This means the resolution capacity of LOFAR is just extraordinary. In fact, we are down at Hubble resolutions. We can get to 0.3 arcsecond resolution capability with LOFAR at these frequencies. It is incredibly time intensive and labor intensive to produce this data. I think, I'm trying to remember what the processing, 200,000 processing hours it took to do one field. So this is where we have to solve some of these processing bottlenecks to make this more doable on shorter timescales. But it is quite amazing what they are managing to see. Just some other random things which you can do with LOFAR. You can actually do three-dimensional real-time modeling of lightning through the atmosphere. And the great news with this is times when you're not looking at the universe because you have a massive thunderstorm overhead. So it's also complementary and it doesn't take up any usable astronomical observing time. But this is also quite, and you have to see some of these in real time, but they're actually revolutionizing their understanding of lightning studies thanks to mapping of lightning over the LOFAR stations. Okay, so what's next? Where you see this plot here is sort of the snapshot of the current status of the field in terms of capability and sensitivity of radio telescopes. What we want to do is, I mentioned we're only really harnessing a portion of the capacity of LOFAR right now. We want to drill down and get our sensitivity and our capabilities to be better than they are now. LOFAR 2.0 will do that. This gives you some of a sort of a feeling for the breadth of science that currently is being done. We're talking transients. I haven't brought up anything about this. We're going to have a very exciting announcement in about a week from now to do with pulsars, and a lot of that work here is being followed up with LOFAR. The high redshift universe, obviously, we're still diving down on the epoch of reionization. This is something which will do a lot of the pioneer work, and SKA will, of course, follow up with. AGNs, I mentioned exoplanets already. In addition to this, and I haven't even touched on it, other than lightning, of course, we have space weather. This is an ongoing societal impact science that we can do with LOFAR, and the monitoring and the technology there is a really, really vital need. Particularly in the era of Elon Musk's and the joys of all of those satellites up there. Okay, so what are we actually upgrading? Well, right now, because we don't have the network capacity, we can only look in that low frequency band or the high frequency band. We cannot do both. One thing LOFAR 2.0 will give us is the capacity to do both at the same time. So we can do dual beam. This is incredibly powerful, especially if you're going to have transient monitoring. So that's very exciting. We're doubling the number of receiver channels. The improvement in the clock timing is going to enable us to get far better calibration, the linearity as well. So most of these are hardware developments. The Cobalt is simply just the processing correlator, so that will also have an improvement. This is our Bungalow test station. We actually have just finished the work to test this at Astron. We now have them out in the field. So the LOFAR stations will begin to phase these in. And the next steps are, we actually purchased everything just in the last few months. We are on the timeline for completion of the entire project by 2025. We opened our large program call, so I needed to change this slide. We actually only did it 2 weeks ago. And so now the problem is, what do we do with the data? We are going to have this incredible capacity of order of magnitude improvement in our sensitivity, and also 2 orders of magnitude increase in our data rates. Right now, LOFAR produces about 7 petabytes per year. LOFAR 2.0 will produce 70 petabytes per year. And yes, that keeps me up at night. It is definitely going to be our major challenge. In the meantime, we're becoming an ERIC. And so right now, the Netherlands is in sort of a loose agreement with all of the other partner countries. There are a lot of things which will be streamlined and improved once we are an acknowledged European research infrastructure. This actually is the better map that I was talking about of where we have the current and future stations. And one of the most exciting new baselines you can see here is, of course, we're going to get Bulgaria in the mix. That's going to be a lovely, beautiful additional one. In fact, one of the interesting ones in the Lowfar family meeting came up, and they're actually calling it the Belgian Hole, which is a great name for a bar. But it actually turns out that the most valuable place for us to put another station is actually in Belgium. This gives us an intermediate frequency space in the UV plane that will be very helpful for us. So it's not always in interferometry obvious that you just want to put them as far away as possible. The distribution is very, very key. But this is a very, very powerful network already, and getting it into an ERIC status is just going to make the collaboration simpler, more streamlined, and we can go for EC funding more easily. Okay, I'm going to switch tack now. We also are committed to the SKA. This is going to be the world's largest radio telescope and operational in its first phase by about 2028. We are actually the Netherlands lead for the regional center development. So this is similar if you work with Alma to sort of the regional Alma nodes, or that is the hope. And that any one of the member states for SKA will be able to be a regional center, but Astron will be leading this. And as I mentioned, construction is now underway. This is mostly still correct. I think I haven't got any updates here. So you can actually see we are an intergovernmental organization similar to ESO. Expected that this is a 50-year minimum project, for an operation. And it's very, very broad in its commitments across the world. We actually can confirm here, Germany has definitely already confirmed on this, and the rest of these countries are all ongoing in becoming members. So we already have some funding to develop our regional center, but we have really got to be the data center for the future of radio astronomy in Europe at Astron. To give you an idea of what we're going to be needing, and I mentioned some of those numbers already, we're probably going to be needing to have an increase in capacity for our data development of a minimum of 6 to 10 petabytes per year in order to handle the amount of data that's going to come out of both Lowfar and SKA just through the Netherlands. And that's at our percentage share of SKA, which is 2%. So the data rates out of SKA will be approximately 700 petabytes. And that's not raw data, by the way, that's reduced products. So we know that we can't do this alone. This is going to be a massive undertaking, and this has to be a coordinated development effort and supported effort across Europe and then across the world. So with Lowfar, we are trying to establish some of these distributed data networks now. And that way, when we have, we're only a few years out from the SKA first data, we maybe already have figured out what works and what does not. But it will be this data processing that will be our limiting factor for our science at all of these wavelengths going forward. So we have to solve this, and then we can solve the rest. So this is why Astron is at a bit of a turning point. Right now, at Astron, we host 2 ERICs and an international governmental organization. And that's on top of our task, which is to make radio astronomy discoveries happen. So we really had to sort of take a deep breath and say, all right, what are we doing? What are we doing right? Where do we need to go next? So this is where I want you to sort of start thinking with me, and I want to sort of give you a scope of what I think the radio landscape is going to be coexisting in about 5 years from now. It's kind of crazy because we're in the world of billion-euro projects. You can't really do anything now and be at the cutting edge without spending this kind of money. And now you think about it, we're going to have ELT on Sky. We're going to have Vera Rubin on Sky. We're going to have SKA. All of these are in this concept phase of about this amount of money. It's going to be all Sky, high data volumes all the time. This is the era in which we're trying to say, well, where do we need to be? Because we don't have €1 billion in our pocket. How can you still remain valid, vital, keep your scientific community agile and adapting when these massive projects are underway. And just in the radio astronomy era, you're going to have all of this different stuff on the sky. We're going to have LOFAR, SKA, low and mid. And then you also have projects like this. And this is more now on the decade scale, late 2020s, early 2030s. ngVLA is going to be also there in the US. DSA 2000, which is also in development, is going to be on sky. When you put these projects together, we're talking about 3 billion euros worth of investment in radio astronomy, 2 orders of magnitude more than that are in there now. So you've got to ask yourself then, imagine the discovery space which is going to be opened up at these invisible wavelengths with this level of investment. So that's why I'm saying that the 2030s are going to be a radio astronomy renaissance. And I do compare it in some ways to the Alma submillimetre renaissance that was opened up. Before that, you know, those 6 submillimetre astronomers on the planet really had a stranglehold on what they could do. But once you had Alma, once you had pipelines, anyone at any wavelength could come in with their favorite science and object and get Alma data. SKA and arguably LOFAR can do this now too. Radio astronomy has always had a high barrier of access. Interferometry, calibration techniques, the processing requirements. It really was a few bespoke people who could do this, and that was it. I always ask any astronomer, like, would you come and use LOFAR? They'd be like, I wouldn't know where to start. And that's bad, right? Because they're very proud of being open skies. It's like, well, you're open skies for the 5 people who can figure out how to use the data, you know, and that's not okay. Especially in these requirements here in Europe and elsewhere, fair data access, easy data access. So really what we have to do to be viable in this future landscape with these big projects, you have to drop that barrier of access down to the ground. You need to make sure anyone can possibly access and use the data from these amazing telescopes, and particularly ones like LOFAR, because the radio astronomy community is going to expand because of these facilities. And so if you want to be competitive and if you want them turning up with us instead of somewhere else, we need to make sure it's worth their while. The other thing is we're already realizing with this expansion, we don't have enough people. ngVLA is hiring, SKA is hiring. We've just got this huge, big new data center in Germany. And I'm worried about keeping my people. Not only that, I'm worried about getting people in the door. We need to expand our workforce by, and I've already calculated this, a factor of 10. So we need 10 times more radio astronomers, software engineers, technicians, developers than we have now. Otherwise, we're just going to cannibalize ourselves and we're not going to get any of it done. So the scale up is huge and it's going to have to happen really fast. And I've been asking this question of myself, is bigger better? Right? We have a 2% share for 40 million euros. The Netherlands has a 2% share. The highest percentage share in SKA from any European country is 6% in Italy. So that's the, and it's not open skies. That's the percentage of time you get. So this doesn't seem like a lot. And it worries me because this is not enough for our communities. We have to make sure that we're providing these other aspects like LOFAR, and we can't do everything to everyone. We can't parallel develop these regional centers. We have data bottlenecks. So where do smaller research communities fit in this landscape and how do you stay competitive? So we went and embarked, I grabbed a bunch of my geeks at Astron and we went roving around the Netherlands. We sort of had these town halls where we sat with the university groups and sort of said, where are you guys at? You know, here's where we're at. And this hadn't happened really before. So it was a bit revolutionary. We actually had Google Forms where we solicited concepts for where would you like to see Astron invest next? And it went really well. We had about 300 attendees over 5 sessions, about 30 different concepts that came out of that. So we then handed this off to a group in Astron and they sort of sat down and they pitched projects to each other, figured out where our limitations were. And we had this report that came out that sort of has a draft for the directions that we could go and what we can do. And we have just had this endorsed by the Dutch radio astronomy community. So this was some of the things we considered. We know LOFAR now, we can get this into the 2030s, even though some of the Dutch stations are kind of melting into that swamp that I showed you there. We're trying our best to keep the maintenance up. With the new LOFAR 2 electronics, we think we can push into the 2040s. We have a solar minimum coming up. This is very nice, right, in terms of low frequency astronomy. And We also know that even with LOFAR 2.0, we have already done the expressions of interest for our large programs. The ambitions already exceed what we're going to be delivering with LOFAR 2.0. So we know if we want to do all of this science, we do have to enhance LOFAR beyond its current capacity. So one of the things we considered is once we do the 2.0 upgrade, the next data bottleneck is our network. It's a 10 gigabit per second link now. Just by doing an upgrade to 100 gigabits, you get an increase in the field of view for both our low and high band of about a factor of 2, maybe even 3 to 4. And you get an order of magnitude increase in our station-formed beams when you use them just singly. So it's very, very powerful for a very simple change. And so what we're proposing for our next grant round, which is going to be at the end of this year within the Netherlands, it's about a 3 to 5 million euro stand. So it's not much, but you have to be very clever with your usage here. So we're proposing a network upgrade that I mentioned. The problem then just knocks down. So I said to you, we're at 7 petabytes now, we'll be at 70. This network upgrade will take us up to 700. The same as SKA. So again, where does the problem then end up? We can't afford to take any data because we can't afford to process it and we can't afford to store it. So the real data bottleneck is in the pipeline processing. You have to go to near real-time processing. You have to professionalize your high-performance computing. We can't afford to keep this data. All of the other countries in SKA are investing, for example, in Germany, it's 1 billion euros in a data center. And I argue that's wasteful and the impact is terrible. What instead, you make sure that you reduce that footprint of data down as early as possible because we can't afford to take data at these rates. But we're also looking scientifically at where else you might look. And this is really exciting stuff. So I told you we have the solar minimum coming up around about 2030. One of the things which SKA is not doing is pushing down in the low frequency below 50 megahertz. Some of the most interesting science that is coming out of LOFAR right now is at some of these lowest frequencies. I didn't even think it was possible to get something sensible with the ionosphere beyond 10. They are mapping at 10. What if you push down lower? What does the sky and discovery space look like between 5 and 50 megahertz? We don't know, but we have the infrastructure there that is a relatively small investment to push to these low frequencies and see exactly what is possible. So we're talking about LOFAR low. We're not going to call it LOFAR low. Find a different name for it. We would need an enhanced LBA antenna. This is this would be entirely cornering the market on this level and this frequency space. The scientific opportunities are unknown. We don't even know what we're going to find. We cannot consider this high risk, high reward because everything you find at these frequencies has not been seen before. You're talking about, fossil galaxies, for example. You can look into the cosmic dawn and cosmic ray origins and transports. There's all these sorts of things that are potentially there, but frankly, we just don't even know. What's nice is it's really simple. All we would have to do is respace our dipoles currently, and we get an order of magnitude improvement in our sensitivity at these frequencies. Right now, they're overlapping too much, and they catch the same beam. So we think we could maybe start to test this out with an RI, but this would really need major future funding. And the main thing we don't know is the ionosphere going to really mess with us? We know it does, but can we model it? Can we move it? Will it actually be the crushing factor that we suspect it might be? But we also think the sensitivity is going to be such that even with just lucky imaging, you might just be worth it. So we're thinking maybe putting a couple of low frequency test stations in this round of the RI, and we can maybe do some feasibility to de-risk some of these. But we also didn't just look in low. It's like we've still got Westerbork. We've got this amazing infrastructure at the higher gigahertz frequencies. How do we look to see whether maybe that's the niche we should be doing something in instead? And so we've got a couple of crazy ideas. And the more we talk about these crazier ideas, the more excited I get about them. Of course, we could just leverage what we already have. How about plonking a couple of SKA mid dishes at Westerbork? Beautiful baseline with SKA mid, north to south, very, very nice already. Also, you get the technology development capacity for, next generation developments. Simple, easy, maybe not as scientifically interesting as some of the other things you could do, but it's definitely on the table. Another one is, I just showed you that map, right, of the LOFAR imprint across Europe. All of that infrastructure shouldn't go to waste. One of the other things we're looking at in these sort of low gigahertz frequency ranges, if you had a dish design, large N, small d system, so now we're talking dishes that are maybe 1 meter across and mass produced, they have ambient, non-cooled detectors on them, and you put 100 of these tightly packed at every LOFAR station. If you did this, and this is where the numbers get quite amazing, you actually get an angular resolution that's better than both SKA mid and DSA 2000, and you get comparable sensitivity to SKA mid. It becomes a very unique facility for high angular resolution follow-up of both SKA mid and DSA 2000. And unlike, and I mentioned those billion-euro facilities, you could do this for about 100 million. So it costs 1/10. So this is a very, very powerful potential future niche that you could definitely use and would complement that radio landscape that I mentioned. So this is sort of distilled now down Astron into the fact that we recognize we've sort of overreached our resources before. We don't want to do this again. We need a solid development plan that will lay the foundations for us going forward. We want to stay operating these amazing facilities like Lowfar and Westerbork. We want to have high impact science, like what I showed you at the start, and we want to keep our cutting edge technology. So we do want to have our cake and eat it too, but we recognize that we can't now do this alone. The scale of these projects is too big. So we do need to start distributing at the work and far more robust partnerships, particularly in Europe. So this is one of the reasons I'm here talking to you today, because these are the sorts of development and projects we really want to see who's interested and who wants to help us with some of this imprint going forward. The other thing, which is a real bit of a shift, it's certainly in the start when I stopped at Astron had been through a bit of a rough patch. Not only just pandemic, before that, you know, they had not really had any leadership, they hadn't been a director in the role for a few years. They're feeling a little bit isolated. So I sat down and had, I think, 16 listening sessions with all of the staff. We asked them some questions, just sat there and heard from them. And one of the things resonated from nearly everybody is that they felt that we had to be more aware of our social circumstance in our communities. We had to give back. And so I sort of mentioned already lowering the barriers of access for radio astronomy, but I want to lower the barriers of access for how we interact in our community. Sort of more socially forward, socially focused astronomy. This is something we need to do anyway. And so we're looking at how we become a leadership role in the North. It's a very poor area. There's not a lot of infrastructure. There's not a lot of industry. And so we're trying to find a way where we're a much more valuable partner and community leader in the Netherlands. And hopefully that's a model which we can look to elsewhere. And so we're looking at how we share our science, our technology, and our facilities. We've got this incredible array of test things. Our wireless data lab, for example, you can see all of these sort of crazy. This is a very, very radio quiet system. And we now have companies that are coming in, developing and using our labs to test their prototypes, for example. We're doing far more outreach and open science stuff with the kids. And we're doing a lot of technology transfer with industry. So these are all things that we need to do more of. The biggest thing I mentioned is that our imprint data-wise is actually going to be our biggest carbon footprint in the future. And we always pointed this out. It's like, okay, let's say we got a efficiency development that gave us a decrease of factor of 2 in our data storage. What do scientists do then? Take twice as much data, yeah? Right? We immediately look to put any efficiency gains into more science. Whereas if you were going to be moral about saying, well, we want to reduce our carbon footprint, we want to reduce our energy, not just cost, but impact, then if you set targets for your impact and you say, we're going to put any of our efficiency gains first into decreasing our impact and our imprint, and then any additional gains we might put into new science, that's a hard sell to scientists. But these are things which are coming down the pipe, even at legal levels, that we have to consider. So focusing on how we make our usage and our astronomy green is now a very big conversation. I'll give you an example here. I just found this out when we were talking about this. Our engineers developed a sensor. And if you pop this on any circuit, it'll immediately tell you the energy utilization of the circuit design. So you can actually use this to make the most energy efficient arrangement of circuit components. And some of the tests they've done already, like some things you can actually reduce the energy use on circuits by, a factor of 10. But our guys didn't make money off this. They just immediately made the design open source and handed it out to the world. And this is an example of where technology increases and improvements coming out of Astron are working towards some of these footprint reductions. So green astronomy, what on earth does that look like? We have to solve these data bottlenecks if we want to take science at this level, but we have to do it green. There has to be a commitment to do it this way, or people will force us to it. We will be ground to a halt. So what we're sort of laying the groundwork for now is all of the industries and all of the prototyping and startups that are working in elements of this. We're saying, let's make Astron a hub for some of this development, because we have all of the data problems at once. So if you look end to end from data collection all the way through to getting a product to people, if you find along the way every single technology data bottleneck that needs to be solved in computing for any different industry, commercial, societal product. So if we solve them for Astron, you can solve them out in the world. And so what that looks like is still being defined, but I think it's actually quite exciting. So in summary, I mean, our mission is to make discoveries in radio astronomy happen, and we're making this broader now. So we're saying we're going to make discoveries in radio astronomy happen for the greatest number of people. That means we have to choose the right projects. We have to cultivate. I don't want to become an experiment that just has one paper come out of it. We want to choose the ones that give the most breadth of science capacity for the largest community. We want to get these pipelines so that we can actually afford to do the science. We want to develop a workforce in our community. We have to start making this community bigger. And I want to decrease the discard rate in our educational systems. We throw 9/10 of our PhDs out in the Netherlands. What a waste, right? We need them back into the fold. We need them as instrument scientists and developers. They don't all need to be doing pure research, but we need to stop throwing them away. And we need to contribute better into our society. This is really something where the disconnect, all of astronomy right now is colonial. And these are problems which we are causing in some seriously inequitable countries because of this. And we don't have any tools in our arsenal to deal with it. So these are problems for our future that we need to be starting to figure out now. So we are deepening our partnerships. This is why we can't do this alone. I don't think any of the countries doing this alone. The joy of radio astronomy is that it has to be partnered. That's interferometry for you. And so I think that you can take that element and you can expand it, and we're going to need to do that. And particularly in this new era with these massive collaborations and these tiny shares in those collaborations, getting these partnerships to where everybody gets something out of it is really, really vital. All right, I'm going to leave it there and we can open up for some chat. Thank you very much.
Thank you, Jess. Are there any questions? Yes.
Nice overview. So as far as I have heard and also read, the calibration with LOFAR is like quite tricky, and the big difficulty is like not a very experienced LOFAR user. If in case you submit a proposal with an open call and it goes through, does Astron provide any sort of like support or help in data reduction or?
Yes, more and more even. So right now our pipeline, we've just released our Raptor pipeline. And this means not only does it do the link calibration, it also takes you through to an image, right? So this is the absolute first guaranteed software in-house that has been developed so that you can just get to your image with an automated pipeline. But we're not just going to hand you the software. Right, we have a team there in our operations center, our science data center, that works with everyone who gets data. And what we're trying to expand now is the capacity of that, because this is exactly what we're going to be doing as a regional center for SKA. So we're already that for Lowfar, but we have to be more things to more people. So this is exactly the kind of thing that we're aiming to do. So short answer is yes.
Okay, thank you. Any other questions? Yes.
Well, you spoke about forgive me if I make a mistake in this, it's a little bit over my level, but you said that Lowfar has like, was going to be 70 petabytes per year. And then like, well, I felt that one of the main points of yours was an emphasis on just how much data there is, how much it costs to keep it and things like this. What kind of like strategies or main solutions how are you guys implementing or planning to implement to resolve this with respect to like the software side?
well, I'm going to say the worst thing, the sacrilegious thing to astronomers, we're going to have to delete data. So this is the challenge right now, is that, every astronomer over a certain age has that drawer, yeah, with the CDs or the tapes in it with that data you're going to get to one day. And I get it. I have them myself. But we are at a point where we can't afford to do that anymore. So one of the, with the current capacity we would have for LOFAR 2.0, we're proposing at Astron that we keep intermediate products, so visibilities, for about 18 months. That basically, I was nearly like chased out of the room with knives at my back for even suggesting that. But the realities are, we have to do it. We can't keep it all forever. And so in that case, you would have this rolling capacity, which means you have to be able to process everything in 18 months. That's all it really does, right? We have to get real-time processing fast enough that we are getting people their final data products in a good form before the end of that 18 months is out. Now, 18 months is arbitrary, but you can imagine that we have to push down to a place where what we're driven by is either we're going to take data for 2 days, and then we have to not observe for, several, a year until we can afford to get more capacity. These are not functional ways to do it. So we have to get that processing robust, and then we have to delete the raw data. SKA is not delivering a single byte of visibility data to anybody. You are not getting any, this is where the Alma model is the same thing. You're not getting anything but your reduced products. Yeah. They can't afford to keep the raw data at all. And the argument here is the repository is the sky. It's cheaper to reobserve than it is to keep the data somewhere.
Okay, so that works for most objects, but what if you're interested in transient?
Yeah, good question. Yeah. And so then you look to the CHIME direction, right? Yeah. What is CHIME doing? CHIME is throwing 99.99% of the data on the floor, right? So you have other models where it's like, all right, if you want transient, you can't have your cake and eat it too. One of the really cool projects that was suggested by the community when we did the Lowfar town halls was take 24 hours of data with Lowfar at full bandwidth resolution. And that was going to be, it was going to take 5 years to reduce 1 day of data at that full transient resolution. But, it would be an incredible data set. If you got lucky though, right? You have to hope that that's the day when something interesting was happening.
Equivalent of a deep field, no?
Yes, it's all of it, right? All at once. And that's sort of the volumes you're dealing with. So yeah, so you have to be agile to the kind of science that you're wanting to take. But the problem is right now, and I'm teasing them, but I mean it. The radio astronomy community is kind of fat and happy. And so the reality that you can't afford to keep all of this data, I think is everyone's sort of in that hard to believe at transition phase, but we're going to have to get to a place where we sacrifice something.
If I may follow up.
Sure.
So if I understood correctly, then it's more about managing and processing that data, those large volumes. Is there anything being done in terms of the software that is used to obtain this data, to optimize or reduce? For example, because I know more of the software side as opposed to astronomy, I know that one huge problem in, let's say, the academic world is that there's a lot of physicists who know basics of programming, but their code is not as optimized as it could be.
That was very diplomatic. Good job.
And I am very interested in this topic. And so for me, is there anything being done with that kind of viewpoint of let's optimize the way we get the data and the way we the way we generate it in the first place? Is there anything being done?
Yes, indeed. And that's a good question. So professionalizing high performance computing in astronomy is essentially what we're doing at Astron now. So we actually have a core team. We're about to expand that. We're going to have an efficiency accelerator hub, and this will solely be staffed with high performance computing professionals, expanding what we already have. And you just have to have robust pipelines. So the pipeline that I just mentioned earlier, this is the first one that will be in our suite. And this way they're properly maintainable. It's not someone's special bespoke code that, you need to require that person to keep updating for 20 years. And you make sure that those foundational building blocks are as professional and as supported as possible. And then you build up from there. Doing the census, as I mentioned, from end to end of where are the efficiency gains to be had? Because now, a gain of a factor of 2 saves you millions of euros. So it's not to be sneezed at to go back and look at the platform and find and get professionals in-house to go and do that work. So that's exactly where we're looking. The scientists belong at the end of this road, right?
Yeah.
And so we're trying to say to everybody, it's okay, you know, we've got to do this in as professional a way as possible. It's a challenge to get everyone convinced on that.
Thank you.
Yeah. So you mentioned that we basically need like 10 times more people, but like the experience, or like what I see very often is much easier to convince people to put money to infrastructure and like say, hey, we're going to do this for science, than actually invest in people, because there's sort of this general trend that people say more people, fewer people are doing more, but they're the same number.
Yep.
How do we get to that point that we actually invest more in people and make more? We kind of like what you said we need actually happen.
Yeah, it's a really good question. And I think, you know, we're having this conversation in the Netherlands, but I know it's happening elsewhere. So if it won't just be astronomy, but anywhere you've run an observatory before, you always lament the fact that governments love to give you innovation funds and hate to give you operations funds. Because it's so shiny, they want to cut a ribbon, you know, and they don't, operations boring. And so it's very hard sell political levels. And this is wasteful, right? Because it encourages scientists to say, well, I'll just drop this toy that I spent 10 years building. And now you've got this gorgeous infrastructure because I'm not going to get it funded, and find a new shiny toy because that's the only thing I can get money for.
Yeah.
And we're having this conversation in the Netherlands right now because we're explaining it's these operational infrastructures which are employing people long-term, who are developing the workforce. You can't do that in university systems where you're churning through people at a rate of knots. So workforce development has to rely on infrastructures. And it is getting an ear in some of these conversations right now. I won't say we've solved it, but there's certainly now more of an understanding that you can put 1% funding onto an existing infrastructure and get gains that keep you up at the forefront instead of having to start from scratch like other places. And that's the same with people. My biggest worry at Astron, they're building data centers in Germany, they're doing development centers in Italy. I'm like, how do I keep my people? Because all of the people you need to hire at those places are at Astron. So I'm mostly, you know, one of the things is like, how do I keep our people in place when they're going to have to start from scratch? So these conversations are finally happening, but yeah, keeping that, accelerating that at the right level will also have to come from the university systems and the university funding. So we do need to also recognize that at the European levels, I think.
Any more questions? Yes.
We will go back then to the data processing, but here is more like a specific. So regarding the international LOFAR stations, so the new vision of LOFAR is going to be like more to centralize the data processing, or to add more independence.
Opposite. We have a data center support now. We have one in the Netherlands, but we also have Potsdam and Jülich. So right now Poland and Germany, is part of their LOFAR contribution. They contribute petabytes of storage and processing space. Italy is going to be the next one on that loop, but we'll be essentially asking all our partners, how many petabytes can you find us? And it's really what we're asking, because, but the thing I want is, I don't want just them being service providers, right? Then they can start to be regional center networks in and of themselves. They can be another user support group, right? Especially for their local users. So in the same way SKA is planning to do this, we want to distribute the problem solving as well. And France is another one with the ngVLA station there, which I didn't mention at any length, but I should have. So we need to be less central. But that's tough sell for some of my peeps at Astron who, you know, they like, you know, being in control of all of this. So that's a challenge, but a completely understandable one. Yeah.
Okay, any more questions in the room? Any questions online?
Don't see any, but hang on, I'm not. No, the chat is silent.
Okay, well then, thank you again for a very interesting talk.
Thank you.
Good night, guys. Pizza will be ready for.
Okay.